All right, where all systems go. Cool. Well, thanks to everyone here that was able to make it. We're going to have a Savic project intro given by Mihailo over here. Before that, I just wanted to throw out some quick reminders. Our spring meeting is coming up. Reminder, it's virtual only. That's going to be Monday, March 11th to Thursday, March 14th, 9 to 11 a.m. Mountain Time on Zoom every day. If you have not registered yet, and many have not, please do so soon, because most of the meeting reminders and things of that sort, I'm only going to be sending to those who have registered, partially as kind of a stick to register. The carrot is that you'll get the information. Also, just everyone already knows, but we have our PyHC 2024 summer school coming up in a few months. Continue to share that. The link is on our website with all the information you could possibly want, including registration, hotel, that NSF student travel funding assistance, which please make sure to share that with all students who are specifically US citizens and permanent residents. The NSF funding, unfortunately, can't do foreign peeps for this one. Let's see. Is there anything else? Nothing big on my end that I can think of. Sean, do you have anything?
Yeah, just a couple things are that one, Savic, which we're just about to hear about, is the newest PyHC project to be added to PyHC. That PR was merged on GitHub pretty recently. And actually, I guess this is a very minor thing, but I can show off very quickly that PyHC is getting a tablecloth for meetings. So for 2 seconds, I'm going to share my screen here. And this is the proof that CU gave us. This is the front of the tablecloth. So if you can imagine just a giant black sheet that's designed to cover a table of like 6 feet long, this would be hanging in front of the table. So you'd have like a black top, and then just right hanging down in front of the thing, you'll see the logo with Python and heliophysics. And it's a nice material. Woohoo. So yep, CU is making that for us, and we'll be getting it here probably not too long. They actually print those out pretty quickly once you pay for them. So yep, that's pretty cool. And you'll see that at the next in-person PyHC meeting.
So excited.
Yep.
Hopefully we can find a reason to throw it up before then, because that probably is not until October or November of this year, but you know, but still very excited. Thanks for taking the lead on that.
Yep.
Wear it like a cape in cold weather.
That's thinking outside the box. That's why
You
we
know,
have
they
time.
did tell us that we had to make sure that we were only using this at meetings for PyHC outreach purposes, but we could probably argue that.
Yes.
Okay. All right. Well, welcome to PyHC, our ecosystem as a whole, Mihailo, and feel free to take it away.
Thank you. So just a second, I'll share the screen. Okay, so this is to showcase the software called Stability Analysis Vitalizing Instability Classification, which is a word salad that I will try to make sense of in the next 20 minutes or so. But basically, it goes to analyzing ion-driven instabilities, and more precisely, linear ion-driven instabilities, which is another word salad that I will previously try to make sense of. What are the physical challenges that we faced trying to do our solar wind research, and then how we turned over to creating this software and this set of machine learning algorithms. That apparently this is an issue that we were able only to resolve by going into this realm and stepping away from traditional statistical and other methods that are commonly used in heliophysics. So, okay, for people who haven't looked into the solar wind kinetics for a while, basically the solar wind expands out from the sun, which is pretty straightforward, and the plasma beta, which is the ratio of the thermal versus the magnetic pressure, increases with the solar winds, with the solar wind expansion, so with the radial distance. And there are several mechanisms that are acting on the solar wind plasma. So you see here a common way of representing the solar wind plasma measurements at 0.3 AU, at 0.9 AU, and further away at Mars distances, 1.5 to 2.5 AU. And the common way of doing it is in parallel plasma beta versus the temperature anisotropy. So temperature anisotropy is defined with respect to the magnetic field direction. So you have, since the plasma is collisionless, it is therefore anisotropic, and you can, therefore can be anisotropic, and you can define different temperatures in direction parallel to B and direction perpendicular to B, where B is the magnetic field. And then you see that as plasma expands, see that's generally anisotropic, and these are very small labels, but it's T parallel is larger than T perp. And then you have solar wind heating, which actually increases the perpendicular temperature only. Then you have the expansion, which increases the plasma beta, which is the blue arrow. And you have, of course, some collisions, which are acting, trying to isotropize the distribution to push it back to the thermodynamic equilibrium. So all these processes, they do act at the same time, but they do act at a different time scales. However, the solar wind cannot live on this plot in all states. There are these lines, this curve, not this straight. The straight are just the adiabatic lines, but these curves, non-straight lines, are the actual thresholds of linear instabilities. Whenever you surpass any of these lines, the plasma becomes dynamically unstable, meaning that there are some waves, some coherent electromagnetic fluctuations which are being emitted from the plasma. And this is how the energy is pushed out, so the plasma can go back to what we call a marginally stable state. So the instabilities are not going to bring back the plasma to equilibrium, but they are going to act as long, every single one of the stability is going to act for as long as it is necessary for plasma to become stable to that respective instability. So it is going to push you within the boundaries of these lines. What's our data set that we initially started to work on? Now we are expanding it, but this is enough for purposes of illustration. So Helios 1 and Helios 2 missions were flying for a total of 15 or 16 years between 0.3 and 1 AU of distance from the sun, so between Mercury and Earth, pretty much. And they measured the velocity distribution functions. So how many particles, as a HIPS are showing, how many particles we have at any given velocity on any given coordinate axis. And you measure most of them on what we call the proton core. So these are the protons, and this is the proton core, so the thermal protons. There is also the proton beam, which is measured over here and given by the red dot. And there are also alpha particles that we can detect in these instruments. So what Teresa Dorovchova did in her amazing work on Helios mission was to take these distributions and to fit them with up to 3 generally anisotropic Maxwellians. So to fit them with the shapes that you see on this figure over here and on the cartoon on the bottom. And then we can differ parallel and perpendicular temperatures for both proton core, proton beam, and alpha. And we got what you see below is a very rich data set of all the 4 possible combinations. So core only being detected, core and the beam core and the alpha particles, and finally proton core, proton beam, and alpha particles, all 3 of them combined within these observations. So what do we do next? Well, we do what's called stability analysis. And we do it with the softwares called the dispersion solvers. So dispersion solver works as follows. You take the solar wind velocity distribution parameters, which I here call P. So it's plasma beta, it's thermal speed of the protons. And then for every single component, you have their density, temperature, perpendicular and parallel, the drift of beams and alphas with respect to the core population, the relative mass, the relative charge. And then you take your favorite plasma physics textbook and you calculate what is called the dispersion relation. So the dispersion relation is a set of solutions of this determinant of the matrix given above. And every set of a solution is a given wave mode. So for people who haven't touched this in a while, basically wave mode is any type of fluctuations which is quote unquote allowed to propagate throughout the plasma. So if any kind of, whenever your plasma particles are pushed back and forth, they're going to resonate, they're going to move back and forth with a given frequency and with a given wavelength, which is the inverse of the wave number k. And those modes can either be stable or unstable, meaning this omega frequency quantity is complex. There is the real frequency at which the particles also oscillate, and there is what we call gamma, which is the growth rate. If the growth rate is below zero, which as you can see on the solution is for vast majority of modes, then the wave is damped, and this fluctuation is just going to die out in the plasma. But if gamma is above zero, then you have what we call an unstable mode, and therefore particles are emitting energy back to waves. So this is well known and done for a very long time. But the upgrade which was brought by Chris Klein in 2017 is that he set up this contour integral. So the contour integral over the unstable realm in omega r gamma space. And we are practically integrating over all the possible unstable modes. And if you normalize that integral properly, then the result is 2 pi times I times the number of the unstable modes. And you can say, okay, there are 3 unstable waves within, say, this distribution. Okay, then what I can do is I can increase the border given by these horizontal blue lines, and I can decrease the domain of integration as much as I want until there is only one mode left. And in this case, this is this non-propagating zero frequency mirror mode given here. So this is what we call the most unstable mode. And this is the mode that emits most energy from plasma particles back to waves. So I can take this mode, and I know at which frequency it operates. I can put it back into the regular dispersion solver, which is called Bloom, and then I can get the frequency, the growth rate, the wave number of propagation, so the direction of propagation, the wave vector of propagation, so direction of propagation, all the eigenfunctions, the fluctuations of magnetic electric field, the velocity, the power emitted, and the fluctuations of density that are associated to that most unstable mode at that given wave number. And this is a large set of data for every mode, which I'm going to call W. So the P is the input, the velocity distribution parameters, and the W are the instability parameters, which are the output of dispersion solvers. And then we did this for Helios dataset. So we repeated this procedure 1.5 million times, which is a lot. And it took us about 8 million CPU hours to do that. So it is a fairly comprehensive work. And when you have something which has multiple radial distances on which it's measured, your natural reflex is to just go ahead and pin your data out over with radial distances. And that's exactly what we did. And we found that as you move away from the sun, so on x-axis on the left panels, it is a distance from the sun in astronomical units. So Earth is at the right-hand side and Mercury is at the left-hand side. You see that there is, for each of the bins, there is less and less unstable intervals. So closer to the sun at 0.3 AU, there's about 60% unstable intervals. And then you have this radial trend decreasing to get to about 30% or so. The gray areas are the parts where we don't really trust the Helios instrument. But there is definitely a linear decrease. There is also a linear decrease in intensity of our ion-driven instabilities. However, there are usually smarter ways to organize your data. For example, with the Coulomb number, which is basically the estimated number of Coulomb thermalization times for any given plasma parcel. And this is the collision frequency times the time of propagation, where time of propagation is roughly radial distance divided by solar wind speed. And when you do that, you see that there are basically three well-distinguished realms. There is the very collisionally young solar wind, which has about 85% of unstable intervals, and which are all very, very unstable and emitting a lot of energy. And then as collisions start kicking in, there is an exponential fallout down to the place where there is after the plasma is to the most effect thermalized, it is barely 20% unstable, and the amount of energy which is emitted is very low. And okay, we said, okay, this is very nice. This is statistics. Let's go ahead and understand the physics of this. Okay, sorry about that. And this is where we ran into problems. So as I said, that we have three basic setups. Sometimes we only have core, sometimes we have core and the beam, and sometimes we have core, beams, and alphas. So when first we looked, because it was easy, to the subset of data which only had a single Maxwellian population. And when it comes to ion-driven instabilities, you can actually analytically derive the thresholds for four basic instabilities: anisotropy instability and mirror instability if the perpendicular temperature is larger than the parallel one, and for the opposite case, the two of the fire hose instabilities, parallel and oblique. And if you look at the left panel, this is what we were easily able to do. And then you can go ahead and you can classify which instabilities are important for each Coulomb number, so for which collisionally young and which collisionally old wind. However, you put in beams and alphas, and then you look at the stability analysis, and all of a sudden these analytical thresholds don't mean anything. So there is a lot of contribution from both beams and alphas, which are mixing out with the contribution of the core. And we couldn't figure it out. We couldn't make a map which is equivalent to the one on the right, which includes beams and alphas, because we didn't really know where to start. Every single P component has increasing number of dimensions, increasing number of parameters, as you can see here, up to 30. And the W component, which is the set of instability parameters, most of which are vectorized, has up to 30 components. Of course, some of these are fairly straightforward, like the mass ratio and the charge ratio. So I worked out the last effective number of dimensions, so to speak. So how many dimensions of data, how many data parameters are affecting your stability analysis? And as you can see, the number is kind of acceptable for the core, but then very quickly becomes insanely high. And I tried plotting various different scenarios on trying to figure out what is the major physics behind all these stability and instability scenarios. But because I cannot plot 30-dimensional space on a 2D screen, and I cannot go through all the combinations within a finite amount of time, and no human can, then we ran into the problem of just not being able to process the massive data set that we have. Also, even if we do, every single instability, every single P plus W set of parameters is just a set of numbers. So looking at a set of numbers and looking at your given plasma textbook, you can infer for any given interval what is your physical instability which is acting on that particular measurement. And you cannot do it 1.5 million times by hand. So what did we do? We developed the SAVIC software, again, stability analysis, which vitalizes instability classification. And I hope that this word salad now makes a little bit more sense. So we now analyze the stability of the plasma as described, and we also classify instabilities within the classification determined by the physically meaningful mechanisms. So basically your textbook instabilities. And first thing what we do is we have a Savic predict algorithm, which tells us, okay, this P, this velocity distribution, is it either stable or unstable? Then the second is Savic Q, which replaces the traditional Bloom dispersion solver, which gives you, for the unstable distribution, what is the set of stability parameters. So it gives you your W. And then finally, the novelty is that you can take this set of numbers, and we built a classifier which tells you, okay, for this VDF, velocity distribution function, and for this set of instability parameters, you have, say, ion cyclotron, proton ion cyclotron instability acting for this particular plasma, which did not exist in the previous plasma solver, and it's a complete novelty. So I'm just going to quickly run you through all these subsets. So for example, these are confusion matrices for the Savic P. So this is just a first step that tells you, okay, this distribution that I feed in is either stable or unstable. And this shows that the accuracy of Savic P goes for practically 100% when you have only the core protons, but doesn't fall below 96 if you have all three populations. Then the next step, Savic Q, which quantifies all the stability parameters, has two subsets. So first one is again the classifier. And this is for core and beam scenarios. So you can have practically the core being the population that drives instability, the proton beam being the population that drives instability. And with respect to the magnetic field direction, this unstable wave can either be parallel or oblique. And that comes down to a grand total of 8 given scenarios, but 2 of those are stable. So it comes down to 6 of them. And then this is a confusion matrix for the 6 of these. Of course, physically, there is most of the core-driven parallel instabilities, 10,000 of them, but about 95% of our values is within the diagonal of the confusion matrix. And then for each of these, there are some values in brackets. So for six of these values, this is one value, second, third, and fourth. We built four regressors. So these regressors aim to quantify for any given unstable mode what is the angle between the magnetic field and the wave vector, and what is the power which is emitted for each component. And there are 1, 4, 4, and 8 regressors for every given subset, and the number of regressors is determined by this matrix. So now we know what if the distribution is either stable or unstable, and now we also know what are the major instability parameters. So we do know P and we do know W. And this is the place where I'm going before I go back to Savic classification part. I'm just going to briefly introduce the algorithm so people are up to speed. So basically your P is automatically classified by the software into one of those 4 groups. Then there is this stable, unstable classifier if the distribution is stable, over and out. If it's unstable, then for the case of this is simplified for only core and only beam cases, and then the red dots are basically the other clouds for core alpha and core beam alpha. But you go into the classifier that says, okay, this is either core emitting, beam emitting, either oblique or parallel. And then each of these classifier or set of classifiers has its own regressor, which outputs the W, so the instability parameter data set. And finally, all these are going into the clusters and then being reported out. And I'll circle back to clusters in a minute. What is also important to take away from here is that, as I mentioned, it took us it took us 8 million CPU hours to produce 1.5 million training data set, 1.5 million measurements long training data set. In this case, when you just run Savic on your home computer, it will take you for 1.5 million of your measurements about 7 seconds or so, if I'm reading this right. And you can process entire missions or entire sets of synthesized solar wind data in mere seconds using Savic on your home computer without even going to a cluster. So when it comes to classification, again, this is the plot for the core only. And it's instead of using your trained eye and using all the theory that you find in plasma textbooks, you just plug it into the Savic software, and it's going to give you an amount of instabilities, which are the ion cyclotron, this driven in this collisionally young wind, and then you have very little of the mirror, so there are some intervals above the mirror threshold. However, in this realm, apparently ion cyclotron instability is still the one which acts the fastest and which grows the fastest, and therefore emits the most energy and is the most unstable mode. And then there is parallel and oblique fire hoses which are taking over in the collisionally older wind. And this is because, if I circle all the way back, this is because we have this temperature, the perpendicular temperature will be stronger than parallel temperature. So this is the ion cyclotron instability threshold in the young wind. And then you hit the fire hose instability in the older solar wind. Okay. Yeah. And this was straightforward. But then now, for the first time, we're actually able to make the same classification for the core beam and alpha dataset. So not 4 different types of instabilities, but rather 12. I'm going to skip the intermediate part for the sake of time. And what happens is that now you have all the bluish are the core-induced instabilities. This is basically the ion cyclotron instability and its variation with that also has unstable alphas. Then you have the alphas with alphas driving instability, alphas with absorbing core, and you in the older wind, which kind of take over once the collisions isotropize the proton core. And then you have the proton beams. So beams are drifting away from the core protons, and therefore they do not collide as much as the core protons do. And this is exactly what you see. There is the alphas taking over from the protons, but then you have the various beam-driven instabilities, which just sit there and contribute about the same amount of total energy as you move away from the sun. So they are kind of living in their own realm. And then at the very end, again, you have these fire hose instabilities, which are characteristic for very old solar wind, which are detected here. And this is all detected by the classifier. No hands-on approach involved. And then finally, which is my favorite result from the application of Savic that actually we put it through, is this mode that takes over once when all of the others die. And this is the oblique fast mode, which is induced by the beam drift. So how it actually works is you can organize your data in any way you want. So we know when the beams are, from linear theory, we know when the beams are about a single alpha velocity away from the core, then they become unstable. And then if you, instead of by Coulomb number, you organize your data by the drift. So drift of the proton versus proton beam versus proton core within a given alpha in speed, or normalized by the alpha in speed, you see that all of these oblique modes are living between 1 and 2 alpha in speeds of the drift. And then when you go over to the wind data, you will see, you plot a histogram of those, you will see that basically all the delta B over VA, so all the beam drift normalized by the alpha in speed in the young wind is kept at about 1 to 1.2 alpha in velocity. So the drift doesn't get larger than that. So what's the reason for it? Well, apparently, while all the solar wind plasma anisotropies and the beam anisotropies and the alpha instabilities and all these things are acting out, there is this mode that keeps the solar wind together, that keeps the proton core and the proton beam not to be too far apart in the velocity space, and that keeps the solar wind within the confines of what we observe. And since the alpha in speed changes with the radial distance, meaning that something which was stable at 0.3 AU from the sun is unstable at 0.9 AU from the sun, then this mode continuously acts and continuously brings the core and the beam within the range of a single alpha in velocity in the velocity space, and guards the solar wind configuration as we know it. So now I'm going to go back and to actually try to give a brief tutorial on how SAVIC software is used. So you have a set of normalized parameters that you need to input: your plasma beta, your core anisotropy, your beam anisotropy, and the ratio of temperatures, and so on. And then what you do is you go pip install SAVIC, import it, and you run your input file. So what's going to happen is that your input file is going to call this for every single, there is a core case, there's core and beam case. Given here, you can have core alpha case and core and beam and alpha case. So behind, under the hood, there are these 4 sets of software that you can run manually if you need to, but there is one overarching SAVIC which is going to automatically recognize which intervals go where. And then first SAVIC P is going to tell you, okay, this mode is stable and it is isotropic at a beta of 1, so it's definitely stable. This one is unstable, this one is stable, this one is unstable, and so on. And then for the ones which are deemed to be unstable, you go ahead and you find, this is core only, so no beam power emitted. You find the amount of power normalized to the wave period, and this is something which I'm not going to. There's actually a detailed tutorial and I can explain after. But there is amount of power which is normalized, which is emitted by either core or the beam or both. And then there is the angle which is estimated, and this is the logarithm of angle, which is estimated between the wave propagation and the magnetic field. This is all SAVIC Q, and finally SAVIC C tells, okay, this is ionocyclotron instability. This is parallel fire hose instability. This is the beam-induced ionocyclotron instability with unstable core. This is the beam-induced ionocyclotron instability with the perpendicular temperature of the beam larger than the parallel temperature of the beam, and so on and so on. So every single cluster given here is going to be represented in your results. And this is the output of your software. This is the pandas data frame that you will get. So there are comprehensive Jupyter notebooks that allow you to run every single piece on the code, Shift-Enter-Wise if you don't prefer using the package. There is the version history. Currently, there is a version 1.1. There is source code on the node. There is the detailed documentation on Read the Docs, which explains both the physics and also how you can go into the realm of ion-driven instabilities. Even though you're not an expert in ion-driven instabilities, you didn't go through years of training to recognize them, and you didn't build the plasma dispersion solver, which basically 3 or 4 groups in the world have done so far. So it guides you through this process, and we put a lot of effort in order to make it user-friendly. And again, just to recap, we started from 1.5 million Helios measurements, took us 8 million CPU hours to process it. We found that there is exponential decrease of plasma stability with plasma instability with the Coulomb number. Then, in order to analyze it properly, we built SAVIC software, and from SAVIC software analyzing proton core, proton beam, and alpha particles, we found that core actually run the dynamics of the young wind, alphas run the dynamics of the old wind, and there is this oblique fast mode, which is the guardian of the solar wind core and beam configuration. But again, this is only one application of SAVIC. You can load your own videos and use them for what you want. And I'm going to leave you with this slide, which is a bunch of QR codes for UpJ articles, GitHub, PyHC, docs, and so on. So thank you, and I'm going to stop here and take any questions.
Wonderful. Thank you for that.
Thanks.
Yeah, that was awesome.
Yeah, I appreciate that you went over the paper and the background behind all of that before you introduced the software. That made it a lot easier to follow.
Well, yeah, it's just a tool which is applied for this specific set of physics problems. And if you ever encounter them, I think it's important to be able to recognize and say, okay, hey, this is what I can actually use SAVIC for, instead of going through a year of effort trying to build all these steps yourself.
Yeah. And I don't know if you've been very plugged into what's happening with the Dash conference, but machine learning and stuff like that is going to be a fairly big focus on a lot of the sessions there. So you might look into submitting something for that.
I will definitely take a look into it. When is exactly the conference?
Have you heard of that before? Dash?
No, actually not quite. I'm kind of in my solar wind safe space for quite a while.
Yeah, good conference for you. Data analysis and software and heliophysics.
Yeah, it's new as of last year, so that might be why you haven't heard of it.
Hey, when is the conference happening?
If you
what
go
is
to dash.heliophysics.net, it has the details, and I'll put that in the chat.
Oh, there you
Okay,
go.
great, thank you.
But yeah, it's October.
It's 14 to 18. It's online and in person at ESAC in Madrid.
Cool.
So I did have a question about your package.
Okay.
What other package dependencies are required, especially what other PyHC packages?
You don't need any of the PyHC packages. All you need is pandas, and there is actually a list of dependencies that is given over there, but it's all the common stuff. It's just pandas.
Yeah, it was pretty short. I remember.
Okay, so it's pretty
standard.
standalone. Nice.
Yeah,
it didn't have
it's
any
pandas,
conflicts
it's
with-
NumPy, it's the URL get, because there is a set of the issue that I found was this set of algorithms. There's a lot of them, and when you train them, they come down to a file. The sum of these files is about 70 megabytes. So it doesn't allow you to be within the software, within the regular package software. So what happens is when you install the software, it's like 1 megabyte heavy, which is basically just the textual files. And then when you import it for the first time, it goes on the GitHub, where the last versions of all the trained algorithms are, of all the machine learning entities. And then it synchronizes both the algorithms. It also synchronizes the paper folder. It also synchronizes the tutorials. Everything is up to date from the single place at GitHub, and I'm updating that place on the GitHub continuously. So as long as the engine doesn't change, you don't need to update the software itself. It's just the background under the hub, which is being updated, and every time you import, it goes online, checks, okay, there is something which has changed. There is a better version of this, say, SAVIC Q classification. It's going to be automatically downloaded and just keep on using it.
Any other questions for Mihailo? I'm just curious, since it seems like a pretty well-developed package at this point, do you have any work you guys, I should say, are looking towards in the future to further the package, or is it pretty well?
Oh yes, most definitely. And this, for example, when you look at this, if you were not an instability expert, this looked pretty awesome, but it does have shortcomings. For example, for every single one of these subsets, there is a bunch of different modes that can be distinguished theoretically, which we didn't do with this current approach. But there is a way to go ahead and use all these eigenfunctions, and the combination of those eigenfunctions is going to give you magnetic helicity, is going to give you the polarization of the wave, and so on and so on. And then you can use the combination of these to make much better classification, which is even more physical. The reason I haven't done it so far is because if I go back here, there is this parcel of data at 1 AU, which is very tricky for Helios instruments. It's just they're not transferred. They were made back in the 70s to work at 0.3 AU properly, and they do. But when they go over to 1 AU, the resolution becomes very low, the range is not good, and so on. So what I did is I went to the wind mission, and wind mission is the one that is over at L1 point, right next to Earth for 30 years now. It has a very rich data set of distributions, exactly in this realm. It's 5 million or so, and they are processed and fitted in both of these scenarios. So both proton core and alphas, and cores and beams and alphas. So I processed about 5 million of those so far on foot using traditional dispersion solver. So for SAVIC 2.0, what we intend to do is to add this training data set, which is going to be 7 times larger than the one, 7.5 million, so 5 times larger than the one to have right now, and then to add this additional physics. And then this is going to be way richer, way more user-friendly, and all of these instabilities are going to be literally nailed down, at least we hope so, to what is written in the textbook. Now it is mostly to what is written in the textbook, but there are some different textbook instabilities which are clamped together because of the lack of data to train the algorithm to separate them. But that will probably be a non-issue once we get to 7.5 training testing dataset size, which covers this 1 AU part, and then we add this additional physics. I tried adding it before. The training data set wasn't enough. When you give it too much data, then it gets confused. It actually gets worse, not better. And I'm sure that pretty much everyone on this call can sympathize with that experience. The analysis is ongoing. I processed about 5 million so far, and there is about 20,000 every day that we add on Arizona high performance computing cluster. So should be probably around next year or so.
Awesome.
Yeah, next year. So yeah.
Very cool. Any other questions? All right. Thanks, Mihailo.
Pleasure. I'm going to stop sharing here.
And
also, there is one thing that I actually, if we have another few minutes of time.
Yeah, go ahead.
we do.
Yeah, there's actually one thing that I always try to share looking in when I present this software, even though nobody ever asks. So this SAVIC acronym actually looks strangely like a Serbian last name. And the reason for that is very intentional. So this name is constructed as an homage to the First World War warrior Her name is Milonka Savic, and she was the first. She was I'm Serbian, as some of you know. So she volunteered to First World War into the Serbian army disguised as a man, and she actually managed to hide it until the first time she was wounded in the chest, and therefore obviously the doctors have discovered. But then she moved on, and she moved on to fight, and she moved on to become the most decorated female warrior of all time. She was decorated by every single country that participated in the war. She is the only non-French person that received the French Legion of Honor, both as a soldier and then again as a commanding officer. And considering the world we live in, somebody being decorated by the Russia and the United States at the same time is probably something that is not going to happen within our lifetime span. And she was officially the first female warrior in Serbian army, the first female warrior as far as we know in the First World War. And she actually moved on to become an inspiration to many people that came after her. The Savic software came out exactly 50 years after she eventually passed away at the age of 84. So there is her short biography over at the Read the Docs Savic tutorial, but I would encourage everyone to go ahead and read a little bit about the life of this truly inspiring personality.
Yes. I remember
So I'm
seeing
going to
that
stop
when
here.
I was reviewing your package, and at first I thought I'd almost clicked on a wrong link, and then I realized no, it's the first package I've seen that gave an homage to an awesome person in their software, and I thought that was really interesting.
Yeah. She also after the war, many of her comrades unfortunately, didn't come back. So after the war, she ended up having orphans and kids from her village, and she actually raised more than 30 of them.
Wow. She was so cool.
Oh yeah,
That's
she
crazy.
was talking too much. She was even too cool for the SS Gestapo to kill. In the Second World War, she set up a hospital illegally in Belgrade, trying to help out the rebel wounded people, and they find out, they arrest her, they beat the hell out of her, they put her in a concentration camp. And then there was the German general who recognized the name after a while on the list of prisoners. It's like, no. And he ordered immediate release. He was like, no, I'm not going to be remembered as a man who executed Milonka Savic. No, we couldn't defeat her on the battlefield, and now when she's a lone lady, we're gonna kill her by firing squad. Like, no. And then she was allowed to live.
Well, there you go.
What an
Good
inspiring
history
story.
lesson too.
Okay, so yeah, that was a short digression. Thanks for your attention about that.
Thank you. That was fun to learn about. All right. Well, if there are no further questions, we can go ahead and wrap. And thanks again, Mihailo, for the presentation and the cool history lesson at the end.
Thanks for having me.
All right. See you all in 2 weeks' time, spring meeting. There are names on this Telecon currently that have not yet registered, so please do that. You can find all the usual places to do that. Just go to our website, go to community meetings, go to the spring meeting page. It'll be there. See y'all.
Bye.
Okay.
Thank you. Bye.
Thank you.
Bye, everyone.